This lesson's topic is solving systems of first-order linear equations. This is one of several lessons that will deal with this very thing. And so first let's look into what is an example of n first-order linear differential equations. And that would be anything that looks like this. Derivative of one of the functions over t is some function of t times x1, which is also a function of t, plus another function times x2 all the way out to another function times x sub n, which is also a function of t, plus some random function of t. And you can see that's the general shape. This is a system of linear equations. Rather lengthy to write this, and one would think, is there a more convenient way?
What?
Well, yeah, it would be more convenient if we could write it in a matrix and vector format.
What?
Yeah, well, if we could do that, it might be a little nicer.
What?
Yeah, okay, here's how we do it. So we'll be attempting to find solutions x1, x2, up through xn of t that satisfy this huge system. And the writing, of course, it might not be that big. I was just showing you the general case. If x is our solution vector, A is the square matrix of functions of t, or they could be constants, and f is some vector also of functions of t. We can express this big ugly thing as just x prime equals matrix A times vector x plus vector f.
What do you think?
Well, I think that's a little nicer. So here's an example of what would be called a 3x3 system. 3 equations, 3 unknown functions x, y, and z.
Why?
Well, no, not just y, x, y, and z. So it's a system like this, only in this case the f is the 0 vector because there's nothing added here, here, or here on the other side of the equation. So we can say x, our vector x prime, which is x prime, y prime, and z prime, is the matrix A, which is 1, negative 1, 0, because see there's 1x, negative 1y, and 0z times x, y, and z. So you know how to multiply a matrix times a vector. And then dy dt, y prime, is 1x, 0y, and 2z. So we have the 1, 0, and 2 in this row, and then apply to x, the vector x, y, z. And finally, the third equation, z prime, is equal to negative 1x plus 0y plus 1z. So this is a more convenient way of writing this equation, and will actually help us a little bit towards trying to solve it.
Wow!
Yeah, isn't that nice? So here's another example. This is we call this maybe a 2x2 system, but it also has an additional vector f that's added. So we'd like to write this thing in that same kind of format, like this. It would make it a little bit nicer. You see it?
Yes!
Okay, great. So writing this system in matrix and vector format, then the vector dx dt dy dt equals, now notice where I'm getting these coefficients, negative 3x plus 4y, so negative 3 plus 4, 5x, 9y, so 5 and 9, and then the vector xy, and then plus this additional function, e to the negative t times sine of t, and this one 4 e to the negative t times cosine of t. You get it?
Oh, yes!
Oh, good. I'm glad you get it. So let's see about this one for the system x bar equals a times x, where a is the square matrix 1, 1, 4, negative 2. Verify that x1 and x2 are solutions of this system. So that's interesting. I guess first thing, if it's a solution of this system, we'd have to say, well, let's see what x1 prime is. So the x1 prime is negative 3 times e to the negative 3t, and then 12 times e to the negative 3t, as you see right here. And a times x1 is this vector, 1, 1, 4, negative 2 times this vector, e to the negative 3t, negative 4 times e to the negative 3t. So we'd say 1 times this is e to the negative 3t, and 1 times this is minus 4 e to the negative 3t. So that gives us negative 3 e to the negative 3t. And then 4 times this one is 4 times e to the negative 3t. This times this is positive 8 e to the negative 3t. So adding those two together, you get 12 e to the negative 3t. And this vector, which is a times x1, and this vector, which is x prime, are the same. So x1 is a solution. And similarly, we did the same thing with x2. That's this one. Of course, x prime just is 2e to the t, 2e to the t, in 2e to the t in both slots. And a times x2 would be the matrix 1, 1, 4, negative 2 times this vector, actually e to the 2t, e to the 2t. So it's e to the 2t plus e to the 2t, that's 2e to the 2t, and 4e to the 2t minus 2e to the 2t, so it's also 2e to the 2t. So ax2 is equal to x2 prime, and that shows that that's also a solution. That's probably enough for this video.
Yes!